everybody. Again, let's see how the AI will work today. Last time, I think there were 2 moments that it sort of did not record me or recorded me wrong or so. Let's see how it does this time. Don't ask what the reason is, not an AI expert, I just know some relativity. And,
probably as long as you don't move very fast from
I
the
think,
edges.
well, the thing is, this literally, and I'm not joking, this particular device, right, the AI thingy, is advertised online for people who ride horses, so you can put your horse ride on it. And I thought, well, that's a very niche amount of people who will be interested in that. Honestly, I thought if you have an AI tracking thingy, then why would you only promote it or advertise it to people who ride horses? I don't ride a horse, but I mean, I thought I would think if it can identify a horse and follow it around, then it should also be able to do so with me. But maybe it's because I'm not a horse. Maybe that's the reason. Maybe that's. And if not, well, we'll see what happens. It's an experiment, and I don't think it was too bad last time. I think last time there were 2 times when it pointed the wrong direction, and then it will just point the thing. And I have a remote, so I can remote itself to back to me, or I just walk towards it and turn it. We'll see what happens. Okay, so let's get started. So I hope by last week you have seen online that on Canvas I posted first of all this recording. I will do so again tonight. Posted the synopsis and exercises. This is what we did. This is where you can find it in the book. And at the end of Friday, when we had our tutorials, I wrote down the key exercises and their solutions, so to say. You can go through it. It's a little bit more than just this is the answer. No, I got there because of this and this reason. Yes. So I hope you can make use of that. You might notice that one of the key things that I do when I write down these exercises is what I also tell in the tutorials, and so does Brecht, is always start with writing down your events. Then things become hopefully very clear, first of all to yourself, but also if you're going to write down a delta t or a delta x or whatever, your reader, be it yourself, one of your peers, or maybe me later, you have to understand, well, whose amount of time and whose amount of distance are you talking about? Who is seen by which observer and between which 2 events? If you do not write that down, as in these are my 2 events for which I'm going to the exercise, it's going to be very unclear to yourself, to others, and also for me, and especially with later exercises where there are going to be multiple sets of events going on, you very easily can confuse yourself. So, as a general tip, but well, that's part of the learning process. So, what did we do last week? We went through sort of the history of special relativity, as in we saw that for reasons of electromagnetism, people saw that the Maxwell's equations, not our job to study those, but it did show you just for completeness that from the Maxwell's equations, one can deduce that there exists a velocity that apparently is shared between all inertial systems. For people who have done relativity before, this is usually taken as a postulate. It's true because, well, apparently it's true, but electromagnetism already pointed you there. I also posted on Canvas Einstein's original article in which he derived that. It was a German article, but I posted the English version, and well, the title says it all. Electrodynamics of moving bodies. So, by Maxwell's equations, speed of light apparently is the same for all inertial systems. That means space and time have to play by special rules to make the speed of light come out the same for everybody. And from doing that, I'm not going to repeat it here, you end up with at least 2 equations that tell you if you know the amount of distance here in one frame, one inertial frame, what is the amount of distance in another inertial frame. That was the Lorentz contraction formula. And we also deduced that if you had a certain amount of time happening between 2 thingies in one frame, how much time would the same 2 thingies take in another frame? That was the time dilation formula. So those 2 formulas, all of this is last week. Let's see, track, yeah, okay. What's this, yes? This is one of the 2 formulas. Time dilation, and well, let's put it in L, which is the distance, is 1 over gamma, and depending on your notation, you might call it L0. This should be familiar to you now. Tau means proper time. There's a small pitfall here because sometimes people think proper time is the amount of time for the person who is doing the moving. That's wrong. Everybody's doing some moving compared to somebody. Yes? So, because the way that we typically build up our thought experiments with moving trains or something like that, oh well, that one is moving because that's a train and the Earth is not moving. No, 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 that's all wrong. Relativity is about relative motion. The best you can say is there is a motion between the train and the floor maybe, and the Earth. But don't make the mistake of thinking that the Earth is some special frame and everything moving with respect to it must therefore be the moving person. That's simply not true. So delta tau, the proper time, don't memorize it as the amount of time for somebody who's doing the moving. It's the amount of time measured by somebody who sees some two events happen at the same location, beginning and end of a process. That's proper time. That's another reason why you should write down your two events so you can identify proper time and you know where to place the gamma. Same thing with distance. This is L0, that's the amount of distance, the width, so to say, of an object or process. If you are not moving with respect to the object, and if somebody is then moving with respect to you, that is a statement you can make, relative motion, then the other person will measure this, which is shorter by gamma. This is the space and time stretching that we saw last week, based on this speed of light postulate that the speed of light is the same for everybody. Okay, yes?
What if, like some of the examples, you had like the Earth and something moving away from the Earth, and then like and you want to know the distance between them or something, like what is then the proper distance since you can't be stationary?
That's a very good question. In some of the exercises, chapter 4 and 5 I think, they typically take a spaceship that moves away from the Earth or something like that, yes. And then the question is, well, who's measuring the distance or whose distance is measured?
Yeah, like what is the distance from one observer or another?
Yeah, that again highly depends on the two events. In many of the exercises, there's something along the lines of a spaceship departs and then it arrives at some star or a planet or something like that. And they are a certain amount of distance apart. Now the book could have been a little bit more clear. When they say they're this much distance apart, they typically mean in the Earth and the planet frame. So it's usually just given. If you're going to ask the person on board of the spaceship how much distance there is, they will say it's a shorter distance. Because compared to the Earth and their destination, they are doing moving, that's the spaceship movement. That means they're not measuring this distance, as you see on Earth, they measure a shorter distance. So it's highly exercise dependent. For some people, you might already see that there is some trouble looming on the horizon. Because, well, if you can take you as an example, right? You and I are now in the same inertial frame, different positions, but same frame. And I now start moving with the constant velocity. I am now in a different inertial frame. If we're going to take as the two events, me checking my clock now, and me checking my clock now, a certain amount of seconds away, then I'm measuring proper time, because the two measurements happen in my frame at the same location, namely at my wrist. So that means this will be my amount of time, and you place a gamma there, and that means you see me check my clock, because those are the two events, first clock check, second clock check, you observing how long that takes in your frame, that's this number, that's a bigger amount, that's your time dilation. But let's reverse the situation now. What if, still same premise, you and I are moving, but it's now you checking your clock, move, and you check your clock again, then that amount of time is now proper time, because those two events are you checking your clock, not me checking my clock. So we can also have a situation where the proper time is now yours. And that means the gamma is now your time, and my amount of time is bigger. So you have to be very, very clear, well, what are the two events? My first situation was me checking my clock. The second situation was you checking your clock. Clearly, two different events. That means different gamma placement. Here's the trouble on the horizon. Yeah, but wait a minute. In one of the two scenarios, you get a bigger amount of time. And in the other scenario, I get a bigger amount of time. So who gets the bigger amount of time? Because if I say 4 seconds passed, and you say 5, but if we change clock, so to say, all of a sudden, what did I say before? Me 4, you 5? Okay,
yeah.
Switches around, then it's you 4 and me 5, then okay, but who measures the biggest amount of time? And that's not a statement about measurement, it's a statement about everything going slower or faster, including our own biologies. Who got older? Well, we both got older, but who got older faster? Well, so this formula seems to contradict itself, depending on which two events you take. And that's because these two formulas are not everything that there is to know about space and time transformations between inertial frames. It's only a subset. There's a bigger set, and that's the goal for today. We're going to derive the bigger set of transformations between space and time and two observers. Now that bigger set is also done in the book, that's chapter 6. Chapter 6 does it again with thought experiments, like we did last week, where you have a laser light traveling up and down a train or something like that, and you derive the formulas for that. The book will give you the result. I will give you the result too, just for completeness sake. And then in a moment I'll tell you how we are going to derive it. So, these are the results. Let's take two inertial frames. Let's call them A and B. Suppose that you know the amount of time between two events. Let's make it less abstract. Let's make it two exploding firecrackers. Yes? Those are events. They happen at the location at a particular moment in time. Let's take two of those. Here's one. Firecracker, it explodes. Bang. Okay? Here's another one. 2 meters away or so. It explodes. Bang. Not the same moment. That means two events. The amount of time in some frame B is the amount of time that they measure between the two pangs, and the amount of distance. Fine. There's a delta t and a delta x. If now introduce another inertial frame that moves with a constant velocity with respect to the first, inertial frame A, and they measure the amount of distance between the pangs and the amount of time, they're going to be different. Maybe using these rules, maybe not. But it's going to be different numbers. Question now is, if a person in inertial frame A measures the amount of distance between the two pangs and the amount of time, can we then calculate how much distance and time there is in inertial frame B? And the answer is yes. We will derive this today, but I'm just writing this down now for completeness. What you do, you take the amount of time between exploding firecrackers in frame A, plus minus, I will say something more about that in a moment. The amount of velocity between the two inertial frames. Right, between A and B there is a velocity. Multiplied with the amount of distance in frame A. The plus minus, can somebody just from the formula tell what that means? That's physical meaning. V is the velocity with which the two frames are moving with respect to each other.
So it's going.
Yeah, which direction? Yes. Erik, I think you said in the tutorial last week, you said, oh, but there's a difference between velocity and speed. Yes. Right. A little puristic, not Erik, but generally speaking, when physics we're sloppy about these things, speed is the amount. Velocity is also the direction. This is velocity. And because there's two directions in which you can move with respect to each other, there's a plus minus question there. Okay, this is one of the two formulas that connects space and time to each other in its full set. You know the amount of time between exploding firecrackers, this number. You know the amount of distance between firecrackers, that's this number. Put them together in this particular combination, and what you get back is how much time there is in the other frame, if you know that they have a relative velocity of v. You have to, per exercise, plug in the plus or minus depending on in which direction they are moving. Yes? Ooh. Unit-wise, something is off. Because this should be a time, so that's seconds. And this is seconds. Gamma is unitless. So this has seconds, this is seconds. This is velocity times, so it's meter per second times meter. This is meter squared over second. We should have needed seconds. There's a c squared there. I leave them out all the time because my own calculation c is 1, so I never bother writing them down. But wait a minute, c is not 1. No, that's true, it's 300,000 kilometers per second. If you use kilometers and seconds as your unit system. If you ask our American friends, you're going to get, I forget what it is, 180,000 miles per second or something like that. Different number, same velocity. But if the value of the number changes depending on which unit system, not coordinate system, not inertial system, unit system, well, then might as well choose a unit system in which c comes out exactly as the number 1. That's what we do in theoretical physics. So in my calculation, c, there's no c, it's always 1. So if you see a missing c, please point it out to me. But you can also put them back yourself, right? Unit wasn't right, so clearly a c was missing. You can even tell how many c's. So if you see one missing, by units you can check what it is. But correct me if you see me do it. I'm so used to c is 1, I make a mistake all the time. This is one of them. You know distance and amount of time in one frame, you can calculate the other. But we also want to have a formula that tells you, if you know the amount of time and distance between exploding firecrackers, how much distance is there in the other guy's frame. And it turns out it's almost the same formula. That's this one. I'm postulating this now, we're going to derive it. So it's again the amount of distance, plus or minus depending on direction. Same plus minus as here. V, velocity between A and B system, and delta TA is how much time there was in the A system. Are we missing C's here? Just from the units? I don't think so. This is meters, that's meters, meter per second times second, that's meters. No C's missing. All good. Do you see aesthetics also putting C equal to 1? Because they really are the same. We love our C as 1 in physics. Okay. And by the way, also Planck's constant is also 1. Newton's constant, the gravitational constant is 1. Boltzmann constant, that relates energy and temperature, is also 1. So you get used to it very fast. Okay, but I will try to put them in, or keep them in as much as I can. Okay, these two formulas are sort of the bigger set than these two. These two formulas are all of special relativity. If you have these two, then in principle we're done for the rest of the course. There's literally nothing more, except stuff that you can do with the formulas, and that is what the rest of the course is about. These two are just special cases of these. When does this one apply? Inertial. That's true of all. Everything we do is inertial systems. You are right, but that's not special about these. Delta tau. When does one have a delta tau to begin with? A proper time.
Not moving compared to each other.
All the delta events happen in the same place?
Yes, you need two events that for at least one of the two observers happen at the same location. So if I do have my two firecrackers here, and they explode and they happen to be both of them in front of my feet, then clearly they happen at the same location for me. Yes? Okay. There's not a situation. There's one firecracker here, and let's say the other one is a meter apart. Okay. And I happen to be in the system moving with respect to the two firecrackers, then I could be walking such that at the moment that I cross the first firecracker, it explodes. And I just happen to be moving such that by the time I arrive at the second firecracker, it explodes. It's a very specialized situation, but let's go with that for a moment. Then in my frame that I have attached to myself, the first firecracker explodes at my feet, and so does the other. Yes? So in my frame, the two events happen at the same location. Not for you guys, because for you it's a meter apart or so. In that case, my time between firecrackers is what we call delta tau. That was the proper time. Then this formula applies. What if we have the following though? What if we have the firecracker here and another one here and they explode? Then for you, in the same frame as the firecrackers, they do not explode at the same location. One of them over here, one of them over there. There's distance between the two explosions, not same location. Now I come along again with my other inertial frame and I come walking along. And sure, I cross the first firecracker when it explodes, but my speed is just not exactly what it needs to have the other firecracker explode when I pass it. Suppose that I walk past it first, it was over here, and now it explodes. Then in my frame, also the two firecrackers do not explode at the same location. That means this formula does not apply for neither of us. Now the exercises in chapter 4 of last week all assumed at least one of the two observers had the two events happen at the same location, right? Departure from sun, arrival at someplace else, for instance. But generally speaking, you need a formula that tells you, well, what if things do not happen at the same location for none of the observers? Then you're going to need this one and that one. That's the generalization. Let's make it very specific, the generalization. Let's take these two formulas. And again, let's now go back to the situation where this one explodes and this one does as well. And I'm walking along, and again, I've made it such that the first explosion happens at my feet, and the second explosion happens also at my feet when I arrive at the second firecracker. What is the amount of distance? Let's make me the A observer. What amount of distance between the two explosions in my frame?
0.
That's 0. Okay, so that means in this formula, delta XA is 0. No distance between the two exploding firecrackers. Okay, so this guy is gone. Hey, lo and behold. By the way, delta TA is then the proper time, and then you get exactly back that formula. So you can quite literally see that this one is just a special case of that one, in case two things happen at the same location for one observer. Similar thing going on over here. Suppose that a stick is flying by. Okay? I know, somebody threw a stick, and it goes in a beautiful horizontal line with a constant velocity. Extremely talented stick thrower who can make that work. But suppose somebody was able to do that. I need that, otherwise I don't have inertia frames. Okay? Stick flies by. Okay. How do I measure the length of the stick? Somebody's sitting on that stick, even more talented stick thrower. Somebody's sitting on the stick, flies by. For you guys, a stick is not stationary. And I want to ask you the length of the stick. What you guys need to do is you have to measure where the front end of the stick is in your frame and where the back end of the stick is in your frame. Then you subtract those two locations, and then one has the length of the stick. No hardcore physics here, yes? This is how you were measured when you were growing up. Somebody measured where your feet were, where your head was, distance. Okay. But now the stick flies by. The stick you if I can. You measure where the front end is. You've measured the front end, so you noted where it is in your frame. Then you wait a second or two, and then you measure where the back end is. Then you have two locations, front and the back end. And you subtract them from each other. Well, does one then get the correct length of the stick? The tone of voice says no. I hope you understand that the answer is no. If you're first going to measure, not you, somebody who is not smart enough, so that's clearly not you, but somebody is going to measure the length of the stick, but first measures front end, then waits a second or so, and only then measures the back end. They're going to measure some distance, but not the length of the stick. They made a faulty measurement. Right? So, now I am back to you if that's okay. The stick flies by, and you don't want to make that mistake. You don't want to end up with too short a stick, because that's what happens. You measure the front end, and then you wait, and then you measure the back end, then the stick comes out short. Not because of relativity, not because of Lorentz contraction, because of crappy measurement. You don't want to make a crappy measurement, so what do? You measure the front end of the stick, and you measure the back end of the stick at exactly the same moment. Yes? So if we make for the two events, stick measurements front end and back end, how much time, if you want to do a non-faulty measurement, how much time should there be between the two events? 0. Okay, so that means this is 0. Delta T is 0. Then the amount of distance of the stick, as you see it as it flies by, is delta XA. This is the amount of distance for somebody on the stick. And because you don't want to make a faulty measurement, you do front end and back end. If you are in the frame in which the stick is moving, you make sure that you do a good measurement, make this guy 0. Then you're going to get that in the frame in which the stick moves, that's what you call L. That's the length you measure. this is the length of the stick as it is measured by somebody traveling along. There's a gap in between, rearrange, up, you get that one. Just to show you extremely explicitly that these bigger transformations contain the other ones that we saw last week, just for special cases. Oh, sorry, I hope this guy took you as an
No
example.
problem.
So, these are the ones. It might be right. If I turn my face around, it starts looking for my face. So how does one teach without ever looking at the screen? Hello. Why can I think track horses and not me? Honestly, maybe I should come here with a horse suit on or something like that. Start jumping the little fences or so. These have a special name, and we're going to refer them as such for the rest of the course. They're called the Lorentz transforms. Same Lorentz, same scientist after which the Lorentz contraction formula was named. Lorentz was a physicist, theoretical physicist, a Dutch person, won the Nobel Prize in 1902 for completely different reasons, by the way, it has nothing to do with this. For the Zeeman effect, if you care to look it up, quantum effect. Lorentz came up with these formulas before Einstein because Lorentz saw that there was something off with the space and time rules in Maxwell's equations that we saw last week. And he noticed, just on a mathematical level, that could be patched by making the space and time rules these. So he sort of followed the same argumentation as Einstein did. He saw there's something off with these Maxwell's equations, something doesn't quite look right. And to make them look right, the Maxwell's equations, Lorentz came up with these two. This is why they're called Lorentz transforms. Then Einstein in 1905, in that paper that I posted on Canvas, and he put everything in place. He also found them, but well, that's what you get. If you're the first person who finds them, you get to get them named after yourself. The Lorentz transforms. Comment, these are the transforms if the two events that you want to investigate from different frames are along the x direction. If I place two firecrackers not in x direction but in y direction, one of them is here and the other one is over there, then these two do not apply. They only apply if you look between inertial systems that move in the same direction as where the events are located. Yes. Now in practice, that usually is not much of an issue, because if I do find myself with two firecrackers in that direction, okay, fine, I just rotate my coordinate system to make it the x direction. That's just a freedom that you have, which part do you call x, y, and z. There is a bigger set still, that works no matter which direction there is, but we're not going to bother with those. Not because they're too difficult, there's no new physics in there, it's just algebraically more cumbersome. So if you want, I can write them down, but we'll go with these, and we'll find that the exercises assume everything is along the x direction. So no problem there. Okay, those are these. So what do we see with the Lorentz transforms? Our formulas of last week are just special cases. Let's derive them. Now, here's where I'm going to depart from the book, because the book does this in chapter 6, again by shooting laser lights up and down trains or something like that, using very explicitly that the speed of light is the same in every inertial system. But it does assume that as a postulate, speed of light is the same in all inertial systems, invariant as you like to call it. And this also Einstein did it. By the way, he never did the laser beam across. It's not me. Who's, can you tell? Is it us? Does it come from outside the wall?
Yeah, I think so.
Is the anti-relativity alarm or something like that?
B10 is right next to us, so maybe.
Well, there is this other lecture room over there. I have no idea what they're doing over there now. Maybe they set something on fire or...
Stop.
The fire's gone.
Okay, fire's gone. Okay, good. What was I saying? Everybody got distracted how do you fire?
The speed of light, how they did it.
Oh yeah, Einstein in his article never used the speed of light goes through a train. He used it in a later book as an example, and then people took the example and made it the derivation, and I'm a little bit unhappy with that. No, I am, for didactical reasons. This is also why I'm showing you this other derivation. For one thing, let me briefly mention all three. There's three reasons why I don't like that particular derivation. I think it's good for you to see the other way. One of them is that if you build your theory around the idea that the speed of light must be the same for everybody, around properties of light, then you might get, as a reader or as a student or even as a professional, the impression that relativity is a speed of light phenomenon. That these formulas and all the strange properties of space and time have something to do with, well, with light itself. That's not true. If you go to maybe one of the particle physics courses, you will see that Marcel or Jacco or Katie, they use relativity all the time in their formulas, even when particles decay, having nothing to do with light whatsoever. Now, do you see the didactical fault in that, and not the way that they do it? But if I were to tell you, well, we get this because of speed of light, and then you start using it at a place where the whole assumption doesn't even apply, namely there is not even light in some particle physics, then we're doing something wrong, right? I mean, it's literally like doing something like this. Suppose I have a triangle over here. And I say the following: look, I'm going to draw a triangle. This is length 3, that has length 4, and I'm going to measure this, and it comes out as length 5. That's true. That is certainly not me. Right, this is Pythagoras' theorem. And indeed, this set works. 3 squared plus 4 squared indeed is 5 squared. Okay? Suppose that I will now come along. Look, I have found a triangle in which this is true. Look, it holds for this triangle. And then I say, well, therefore it must be true for every triangle. That would be extremely crappy deduction. You cannot take one example and promote it to general validity. You cannot do it in mathematics. I mean, it is true that this is true in general validity with a straight angle, but you cannot prove it just pointing at one example. But that's what we do at the moment that we say, well, we derive these formulas by speed of light. Oh, and by the way, it's true everywhere else as well. That's simply incorrect. That's one. The second reason why I think it's important to see a different way is that the derivation with waiting for light to bounce up and down a train might give you the impression that your relativity has something to do with waiting for light to arrive at your place. If something walks by here, firecracker, and it explodes over there, and I'm going to measure the explosion of the firecracker, in reality I will have to wait until the light of the explosion hits my eye before I know about it. That's true, but that's not relativity. Relativity is about the thing really exploding sooner or later, depending on how things are moving. But because if you build it around, well, light is bouncing up and down thingies, you might get the impression that it's just an optical illusion, waiting for light to come to you first. That too is wrong. And I think the light derivation gives you the wrong impression, so to say. And finally, very important, I mentioned already at the beginning of the first lecture that special relativity only applies in inertial systems. And nowhere in our derivation of last week, with the trains and the bouncing up and down, did we use inertial systems at all. So right now, you might get the impression that this is also true for non-inertial systems. So there's at least 3 reasons why I think it pays to do it differently. So, what I'm going to do, I'm going to derive the same formulas, not using light whatsoever. So from that moment on, you can never assign it to special properties of light, but we will see it's a property of space and time itself. We're going to finalize with saying we can assign it to the geometry of space and time. You will see that this is not the result of light, it's the result of how literally space and time feed into each other in a geometrical way. And the only thing I'm going to use are inertial systems. No light, no nothing. Okay, so what are we going to do? I'm going to start with 2 inertial systems. A and B, and they have a relative velocity of v. How fast one frame is moving with respect to the other is called v. That number has to be constant, because otherwise one of them is not an inertial system. Okay. Now, in this system, they measure two events, whatever they are, exploding firecrackers, with amount of time TA, delta TA, and amount of distance, delta XA. And in this other system, they do it in their own coordinates, T and B. T and X in B.
Sorry, in A, velocity is constant, right? Is that what you said?
No, that's not what it says. What it says is that between A and B,
Yeah?
the two frames have a relative velocity of V.
Okay.
And there's two things happening. Again, make it two exploding firecrackers, and they're going to measure it in system A and in system B. Both of them will measure a certain amount of time between the explosions and a certain amount of distance. And in this frame, they're going to call it delta TA and delta XA. In this one, they're going to call it TB and delta XB. Note that I'm explicitly leaving open what the two events are. That's a good thing. That means whatever comes out of the derivation will hold for any two events. If I were now to stick in something about light or particle physics, then we come into the issue with the triangle again. I might get a result for one particular example, and then I don't get it promoted to general validity. So I'm deliberately leaving open what the two events are. Makes it more abstract, but makes it also much more applicable. It's not physics related anymore. Phenomenon related. What I would like to do is get a formula that if I know the amount of time between two events in the A frame and the amount of distance in the B frame, that if somebody's measured those two numbers, that I can calculate what the numbers are in the other frame. That's my objective here. So what I want is that delta TB and delta XB is something times delta TA and maybe something with an XA. We don't know yet. Same here. If I know the numbers in the A frame, I would like to know the corresponding number in the B frame. So I know that there's some mathematical rule that turns one of those into the other. I don't know what it is yet. But here comes the magic of inertial systems. I know that this relation and this relation must be linear. By linear I mean the numbers do not appear to the second power or the third power or a sine or a logarithm. They can only appear as themselves. Can people see why that is true? Why the transformations can only be these numbers with maybe something in between, but no squares, no logarithms, literally just the thing itself.
Because the relative velocity is constant.
The relative velocity is constant, sure. How does that make this a linear transformation? I'll let you parse this for a moment. It is true, in a moment I will tell you how and why. Yes? Okay. I will already say this is the only way that this works. Not as in, then that's the only way I get my desired results. I don't know my results yet. Well, I do, but let's pretend we don't. Yes? In a moment, we will see why this necessarily must be true. Well, if it is, then the only combination that one can have is, well, this number times some constant, maybe that number times some constant, and then a plus in between or so, and the same there. I don't get to square or third power or square root. They have to be linear for reasons to be seen in a moment. Well, the most general thing I can do from this moment on is just add a couple of constants in between. I'm checking which constants I chose, because this derivation I've written out for you. And I don't want to make up constants that in my written version I've called differently. It gets confusing. So let me put in my cheat sheet how I called the constant. Yeah, those were these. There's a sigma plus, there's a gamma, and there's a kappa. There you go. So, yeah, I think we've figured out what the problem is. Okay. So these Greek letters are simply the numbers that I don't know yet. And my job is to figure out what those numbers are. And if I figured out what the numbers are, so there's 4 of them, 1, 2, 3, 4, then I have my complete set of transformations. By the way, when I say constants, they can depend on V, or they probably will, because that's what distinguishes A and B from each other. So the constants probably are going to be V dependent in some shape or form. Yes, but they're not going to depend on T and X themselves, because otherwise I break my linearity that I should plug in. Okay, so, yes?
Couldn't there also just be a plus on the end with a constant? Isn't that
Sure.
more general?
As in, you can add another plus something without
Yeah.
T and X. Yes, that's absolutely true. I think it's not going to matter for the rest of the story though,
Okay.
because at the moment that you would do that, you would have 0 time and 0 difference, so 2 exploding firecrackers and A at the same location at the same time. Then what we will be saying is that in the other frame, there will be a certain distance apart. And no, that cannot be the case. No. Mathematically it's true, but physics-wise it cannot be true. If I have 2 firecrackers, for you exploding at the same time and at the same location, that means if you are A, delta TA is 0, delta XA is 0, then the whole thing is 0. If I come walking by and I walk over here, they should explode for me also at the same moment and at the same position.
Oh yeah.
And if I would add a constant, I would lose that.
Yeah.
So mathematically you are right, but you're right. This is disqualified by physics. Yes,
Is A the reference frame where the events are happening at the same location?
that's completely open. I haven't specified the events.
Mhm.
That's again why we're going to get rules that hold for all situations. When I have this, and again I don't know my 4 constants yet, but I can immediately do something beautiful. I can divide them on each other. Then after this I will return to the question, why should they be linear to begin with? I will divide them on each other. So what do you get? You get beta delta XA plus sigma delta TA divided by the other guy, that's gamma delta TA plus gamma delta XA. I get that. Just algebra, no physics at this point. And you know what, let's divide out a delta TA on both sides as well. No physics, all of this is algebra. So, there we go. I literally just took a delta TA out, put it here in the numerator, did the same in the denominator, and I have a delta TA up and down multiplying everything, that's just the number 1. So we end up over there. Algebra, no physics. There is, however, a physical interpretation. Because what is the amount of distance divided by the amount of time? That's a velocity. Which velocity? Well, it depends on which 2 events you're looking at. Had this been 2 exploding firecrackers, this would be how fast you're moving with respect to the 2 firecrackers. I deliberately do not call the velocity between, I don't call this velocity V, because I already reserved that particular symbol for the velocity between the 2 inertial systems. This is the velocity with which you see the 2 events move with respect to U. So I call those U, to distinguish them from the V. I put a label to it, B, because, well, how fast things are moving with respect to U is dependent on which frame you are. So, left hand side is UB. Right hand side, there's a beta. What would you call this?
UA.
It would be UA. It's the velocity of the same 2 events, but now seen by the A person. It's how much distance there is between 2 events in his frame divided by how much time there is in his frame. Well, that's what you call high school physics, the velocity in the A frame. That's this, yeah, plus sigma. And I have a gamma plus kappa UA. I still don't know what all my Greek letters are, but one thing I do know, if these are the transformations between space and time, then these are the transformations between velocities. Let's make it a little bit explicit now. Suppose that a car drives by. Yes? And, sorry, I keep using you, but that's okay. You watch how fast that car is going. What you're going to do, let's make you the A-frame. You're going to measure how many meters per second the car is driving. So how many meters, so let's take as the two events. Pinpointing the car at this location. Second event, pinpointing the car at this location. You measure how many meters in between, that's delta XA. You measure how much time that took on your watch, delta TA. You can calculate how fast the car was moving with respect to you. It's a very elaborate way of saying you can measure how fast the car is going. Okay? Now I'm going to introduce a system B. That's not the car per se. So the car is still going over there. I am now system B, and you and I have a relative velocity v. And I might be moving in the same direction as the car. Maybe not as fast, different velocity, but I'm also moving in that direction. That car, in my frame, will also have a certain amount of distance traveled. It's a smaller distance because I'm traveling behind it. And there's a certain amount of time in between, that's delta TB. So I can measure how fast the car is moving in my frame. The relationship between what you found for the velocity of the car, UA, and the relationship and the amount of velocity of the car that I see in my frame, that's this guy that we found. We still don't know what the Greek letters are, but we have a velocity transformation rule. These rules tell you how your amount of time, your amount of distance are calculated into my frame. This tells you how velocities are going to be different. We still don't know anything because we don't have the Greek letters. But going back to your original question, can you tell why the Greek letters should be constants?
Because the direction of velocity, if we square.
There are no V's at all, are there? No, I'm not bumping your question, I'm just parsing it.
Mm-hmm.
Please?
Is it that, like, if you do any sort of squaring or anything, you get rid of any minus or plus that could be?
I think that's a similar question to what Johanna was saying, that there is a plus-minus issue potentially with directionality. There is, by the way, both of you are right. It's hidden in the constants to be found. So you're right, it's in there. Physics-wise, it's in there, but we haven't found it yet. So the question was, well,
With the additional leftover like time, if we square it, right? We can cancel out like just velocity.
parsing the cancellation. You square it, so you square both sides?
No, why we don't, why
Oh.
it has to just be linear.
Okay. That I think, if I parse it correctly, is close. This formula should hold always, right? What if we make the car stand still in one frame? That could be the case. Maybe you are the car. Then the location of the car every next second is 0. You have a UA of 0, agreed? Then what should my velocity be? If you and I are moving with velocity v with respect to each other. This will be gone, and that will be gone. So let's make a special case. You are seeing the car stand still. Right? That means your UA is 0. Then in my frame, moving with v with respect to you, so this is a special case where UA is 0, car happens to be standing still in your frame, then I will get sigma over gamma, that's what I'm left with. Yes? Inertia frame. Should this number be a constant?
Yes.
Yes, because you and I have a relative velocity of v. I smuggled that in at the moment that I said that A and B are both inertial frames. That means if it goes with constant velocity in one frame, it should also go with constant velocity in the other frame. That will not happen at the moment that sigma and gamma are themselves functions of time and space. I lose my inertial systems. In the the special case, it should always hold, but it should certainly hold in the special case where something is standing still. That means in the other frame it should also be standing still. If it doesn't, then in one of the two frames, Newton's first law is broken. That means one of the two systems was not an inertial frame. And I'm stepping out to find formulas between inertial frames. So it's inertial frames that tells us that this should be the general transformation. If the same argument slightly differently phrased. If I would have had a square here, for instance, and maybe that's what you were hinting at. Suppose that it was a square. And then I would have taken out the delta t, right? Let's put it over there, or where was it? Here, I think. Then it would have been a square over there. Then this guy, that's how fast the car would be moving in your frame if it was standing still. It would not be zero anymore. This would not be the velocity. It would be some sort of acceleration or so. That means in one of the two frames, there's an acceleration, and in the other frame there isn't. And it should be, in absence of forces, constant velocity in both. So, long story short, this is why I know it should be linear transformations. Everything else than linear is going to make one of the two frames a non-inertial frame. And that was not allowed by premise of our exercise. This is also why I said that this derivation explicitly builds in inertial frames. That was one of the things that I said that is nice about this derivation. You can see that all of this will only hold in inertial frames because that's what we plug in. So this hopefully puts in perspective my comment of last week that special relativity, we're going to find here, is an inertial frame theory. General relativity, period 5. Okay. So I hope this is put in place. For the non-Dutch people, curly thingy means great. You know what I'm talking about, right? If your teacher writes this on your paper, it means you're doing well. The formula is doing well. I notice it with non-Dutch people when they say, wait a minute, what's a curly thing? It means going well. Okay, but then we are here. We have four unknowns, four unknown constants. If we can find the four unknowns, we know what beta, sigma, gamma, and kappa are. We can plug them back in, and then I promise you we'll end up exactly there. Well, if you have four unknowns, you have to look at four special cases to fix the constants. That's the nice thing about linear equations, mathematics. If there's four unknowns, you need to apply it 4 times, and each of them is going to set one of the constants for you. I will do a few of them. The full derivation I will upload because it's not in the book, so you can fully go through it if you want. Because I don't care so much about the algebra, I want you to care about the narrative. And if you want to do the mathematics that's written out for you, I'll upload it. You can go through it yourself. But here's one special case. Suppose that UA is 0. In fact, that was the situation just a second ago, that there is this car and it's standing still in the A-frame. Okay, well, then I know that UA is 0, but I immediately know what UB should be. Look, here's the car, standing still with respect to you guys. UA is 0. Special case. We need not have stood still, but suppose that it is. I now come along in the B frame, and let's say they're moving in that direction with velocity v, this velocity. How fast is the car moving in my frame now, if it is standing still with respect to you? That's just v, right? Special case, if you see the car stand still, and you and I are moving with velocity v, then I'm seeing the car with velocity v. So I know that this should be true, that if UA is 0 for you guys, then UB should be this v for me. Oh, that's one of the 4 cases. Let's plug it into our velocity rule. So it says v should be equal, that's this one, to beta times UA, that's 0 plus sigma, divided by gamma plus kappa UA, what UA is 0. So I get v is equal to sigma over gamma. And that has as its result that gamma, or excuse me, sigma is gamma times V. That's good news. Because that means if I already know, and that's our premise of our exercise, we know the velocity between the two frames, V is a known number, that if I happen to know gamma already, I immediately know sigma. So gamma and sigma I can relate to each other. That means if I know, I don't have to look for 4 unknowns now. Beta, sigma, gamma, kappa, no. If I know gamma, I immediately know sigma. So instead of 4 unknowns, I have 3 unknowns now. Good, that's 1 unknown less. Okay, good. 1 down, 3 to go. Now I'm in the car, still moving in that direction. I'm going to measure the velocity of the car. What is the velocity of the car in my frame, the B frame?
0.
That's 0. So, special case is if I now happen to be standing still with respect to the car, UB is 0. What are you guys seeing for the velocity of the car? I hear minus V, that's correct. Because in your frame, I'm moving in the other direction. So, special case is if I'm standing still, and that is still my V direction, then you guys should be seeing minus V. Second special case. Thank you, including the minus. Okay, let's plug it in, see what happens. And UB is 0. It's equal to beta times UA, but that's minus V, so that's minus beta V plus sigma divided by gamma plus kappa, unknown, but I do know UA, that's minus V, I get this. I have a fraction. And fractions being 0 means the numerator has to be 0. Yeah, unless you are in a crappy situation, the denominator is also 0. If you L'Hopital your way through it or so. But that means that sigma must necessarily be equal to this. Isn't that nice? That's again a constant less, because if I know 2 of the constants, I can calculate the other 2. In fact, you can combine these to each other and see that beta and gamma are actually the same thingy, whatever it is. So we're slightly peeling down the unknowns. So it's pretty good. I will do one more, and the 4th one I will mention, but you can read it in the upload that I will give you. Here's a special case. What if I do the following? I'm in system A, and I'm then going to coordinate transform whatever I see happening in A to system B. Lo and behold, I'm going to coordinate back again to A. So there's an A frame, you guys again, there's a B frame, that's me. Whatever happens over here, car, whatever, exploding firecrackers, your numbers get transformed into my numbers, and I use my numbers to calculate back your numbers. Then I should get back as if I never transformed at all, as if we never jumped back and forth between. Yes? Coordinate transforming from A to B and then back from B to A should give you the same as if you never coordinate transformed at all. That's a 3rd condition. The constant should be such that if you jump back and forth, it should give you the same as if you never jumped. This is abstract to you, let's make it very simple. I'm standing over here. I'm going to coordinate transform to this position, and I'm going to coordinate transform back. If you would have had your eyes closed, you could not have seen that I did that. Yes? That's simply what I'm saying. Let's linear algebra this one. those two transforms that I started with, I can write as a matrix equation. What should be put here? Something should be here such if you write out the matrix equation, you get back our starting. So what goes where? Right, gamma times delta A plus kappa times delta X gives you this. And the other one?
Sigma beta.
Sigma beta. Same set of equations, just written down in a mathematical shape that makes this step slightly easier. Okay. Now let's put on our linear algebra hats. I now want to transform back. Transform back now. What should the matrix be?
Matrix again.
So it's called the inverse matrix. If this guy tells you how to go from A to B, then linear algebra teaches you what this matrix be to make you go from B back to A.
Beta. So it's beta minus kappa minus sigma and then gamma. And then
Something like this? Yeah.
Shouldn't there be 1 over the determinant as well?
Agreed? This linear algebra. The inverse transform is 1 over the determinant of the original matrix, which is gamma beta minus sigma kappa. There you go, and now we're complete.
Should be A.
Help me out here.
The first
I'm
two.
doing something wrong. Yes. A and A.
Also the AI.
Yes. So maybe you look like me now. The AI, yeah, that's it wrong. I don't know. Maybe AI really doesn't like linear algebra or something like that. Oh look, it heard me say this and it started to move away. Well, that was 300 euros well spent. Okay. Okay, so I will not write out the, well, let's do one more step of this. First of all, do you agree that this number cannot be 0? Because you will be dividing by 0 and that sucks. Because you're going to get infinities, which means in one frame the amount of distance is 5, in the other frame it's infinity. Well, that will be physically something we certainly would not like. So there's at least some combination between the 4 unknowns that says it should not be 0. Okay, but what should it be? Oh, wow, okay, why is that?
Because you wanted everything to stay the same.
Yes.
Is I telling out it's steeper changes?
I agree. That's a step that I wanted to write down, but here we are. Let me paraphrase it, that's okay. The number should be 1. Not just none, it should not just be non-zero, it should be 1. Because that's exactly that step that I made. If you transform to one frame and you go back, you should get back to exactly the same thing, but the determinant is going to scale things up or down. And scaling is fine between frames, that's relativity at the end of the day. But if you go back and forth, you should get back the same. I want to write it down in full, and for the people who want to do that, you can still do it in the following way. Delta TA, delta XA, well, that's this guy. So you can replace this by that. Then you're going to get delta TB, delta XB, matrix, 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 delta TB, delta XB. And that whole bunch in between should be exactly 1, the unit matrix. Because you want delta TB to be equal to delta TB. You want delta XB to be equal to delta XB. So if that's really what you were saying, but for the people who want to see it explicitly, plug this. So that's all of that into here. You're going to get a matrix multiplication and determinant, but you know that whole bunch should all be the unit matrix. If it's not the unit matrix, you will not end up where you started. If you write that out, you will explicitly see that this combination needs to be equal to the number 1. So, without writing that out, here's another condition. And we box all of them. We have now 3 conditions.
Doesn't the last condition make it 0?
Yes, you're right, and you are right. This should be 1. That's exactly why. Thank you very much, because I was saying it should not be 0, because then things blow up, etc. Okay, so first condition gives us a relation between the 2 unknowns, the 4 unknowns. So effectively, it means you have 1 unknown less. Second one, relation 1 unknown less. Third one, 1 less. And at the end of the day, we really have only 1 unknown. If you know 1 of the Greek letters, then with these 3 box equations, you can calculate 2 of the other ones. Just need to have the final one. This one I will not write out. It's algebraically a little big, but I will mention the argument. And again, the full derivation is uploaded for you. It's as follows. I'm going to introduce a third inertial system. Well, you know, it's not that bad. And it has a relative velocity of v primed. Prime does not mean derivative, it just means different number than v. And it comes with its own space-time coordinates. Okay? Yes?
This is velocity v prime. It's relative to which one?
To the b one. Yes. But do you now also know the relative velocity between a and c? It's v plus v prime. Yes? And that's exactly the heart of this fourth argument, namely, with the equations that we now have, you can calculate how these guys turn into those guys. That's this formula. You can also write down these formulas if you go from B to C. You're going to get a different gamma, kappa, beta, and sigma, as in they're going to depend on V prime now. But the primed Greek letters are still related in this way. So, this is where it becomes algebraically messy, but stepwise not too difficult. If I'm going to transfer from here to here, and that I'm going to transform to C, I'm going to get one big equation that relates A to C to each other. Yes? That's one way of going from A to C. One other way is completely sidestepping set B. You go from A to C in one go. Its velocity, we just spoke about this, is v plus v primed. So, there's 2 ways of starting in these coordinates and ending there. First one is by using these equations twice. First to go to B and then to C. Then you're going to get one big set of equations. The second possibility is to make one huge step all the way from A to C in one go with their relative velocity v plus v primed. 2 sets of equations should be the same. If you're going to end up in C, it doesn't matter if you first went through B or not. So you're going to get 2 sets of equations, but they should be equal. That's a messy algebraic exercise, but that gives you your fourth condition. Now, again, in the upload you will see how that works, but the strategy should be clear. There's a deeper meaning behind this one. If we would have had said, no, you can only get to C by first going through B, then we would have given some special privilege to B. That B is sort of a mother system where you always have to first go to before you can go someplace else. But relativity says, no, every frame should be equally good. So saying that from A to B to C should give you the same as going from A to C is really just saying that the B frame has no special properties or something like that. Now this is what's called the principle of relativity. No frame has special rights. This is why it doesn't matter to go through B first or take one big step. So that's what I'm plugging in here. There's a deep, almost philosophical reason. The B frame is not special. One does not have to go through B first. I'm not going to write it out. Again, upload it. But if you work everything out, so this one, and the messy one that comes from that one, then you're going to get, so one big expression, everything combined together, you will find that gamma, one of the unknowns that we started with, that gamma comes out as this, the Lorentz factor. Not because I want it, not because I was hoping that it would come out. This is the only mathematical solution to those four equations, those four box equations. That's gamma. We already saw that beta and gamma are the same thingy, so this is also beta. Sigma happens to be equal to kappa, and its outcome is minus or plus, you have freedom there to choose, times V. I'm telling you now, yes? If you don't believe me, take the four equations that we found, the four box ones, plug these guys in and see that it fits all of them. Nice exercise, if nothing to tonight. Okay, so these guys are now found, all four conditions. Plug them back into here, and you end up exactly over here. No light, I just use inertial frames. Going back to my starting pitch, that means these formulas are only dependent on the inertial frames. They don't require that you know that the speed of light is the same. It doesn't require that it's this physics and not so much in that physics. It doesn't require you to wait for light to reach your eye. This must therefore be always true between space and time itself. That's all that I used. I used no physics whatsoever. Sure, in my graphic interpretation I put a car here, but I never used the properties of the car, for instance. Yes? I just use events and inertial systems. So this will hold for all events in all inertial systems, no matter the physics. This is why this derivation is much, much stronger. More abstract, but very strong. I'm waiting for somebody to say, but wait a minute, there's a C there. Can somebody ask? Yes, please.
Yeah, why is the
Yeah, it's a good question.
There's not in there in every.
Yeah, there's a C there. And we never plugged in a C, right? If you plug all of this into the four box equations, you will see that it works no matter the value of C. I'm not saying that this is the speed of light. That light goes with I mean, I can't see that it is a velocity because of units. This is unitless. V is a velocity between frames, so C must be a velocity, otherwise units do not work out. So I know that the C, whatever it is, it must be at least a velocity. I'm not saying that it is 300,000 kilometers per second. I am not saying it has the same value in our inertial systems, and I'm also not saying it's attached to light. So where does it come from? Well, here's an unsatisfactory answer from the mathematics. It is completely standard, if you do a mathematical derivation in physics, that you end up with a few constants at the end of your calculation. If you use Newton's laws, and you say something is flying through gravity, and you solve Newton's equations, you will also end up with a couple of unknowns. The unknowns saying, well, with which velocity did it start, and at what location did it end? Yes. If you, in your physics calculation, have to do something like this, maybe this is part of your physics calculation, what's the answer to this? Am I correct? Let's see. Plus constant. The same happens here. In this derivation, you will find that you have the freedom to plug in a constant. You don't know what a constant is. The mathematics simply tells you you're allowed to put it there. Should you put it there? I don't know, maybe to make it long. That's what I do. So it's the mathematics of the inertial system that says, yeah, but there's a constant hidden in there someplace. And just simply following the mathematics. So again, I'm not assigning any physical relevance to it, I'm simply saying that it's there. And if you don't believe me, plug everything in, you will see that this C drops out of the four conditions. That means you're free to choose a whatever. I'm going to erase this, because you might think, yeah, but it's the speed of light, right? Well, yes, if we already know that this is the outcome, yes. But suppose that we live in a world where we were never able to do experiments on light and electromagnetism. We didn't know that the C was there. As in, we never measured some value of C. Let's look at something beautiful. Ooh, so beautiful. So beautiful. Let's plug in what we have here. So we derived also the velocity contribution, right? How you transform velocities. That was one of our first steps. Plugging these guys into here is going to give you the very important formula that we will use for the rest of the course. It's called the Einstein velocity addition rule. And it looks like this. I'm not postulating this. It's just this equation with our betas and kappas and gammas filled in. Yes. This is the rule that comes out. Well, first of all, you can see that something interesting happens. If we were in normal everyday physics, so to say, then the numerator is what you might expect from things. If a car is driving in this direction with velocity as seen by you guys, UA, 50 kilometers per hour, and I travel behind it with 20 kilometers per hour, so you see the car go with 30, or excuse me, 50, and me trailing behind it with 20, seen by you, then you would likely conclude that in my frame the velocity of the car should be 30. Because every second or every hour I don't see it travel 50 kilometers away from me, because in that same hour I travel behind it with my own 20. Well, that's exactly what this says. Depending on which direction, in our case would be a minus, if I travel behind it. So the numerator is what you would expect on Newtonian physics, so to say. Your velocity and my velocity are different by how much you and I differ in our own velocities, our v's. But according to this rule, no, actually, it gets divided by something. So the number is not this addition of velocities, just add them together or subtract them, doesn't work anymore. That's an immediate consequence of all this work here. Let's now do the following. Let's make that car go with the speed, well, with this unknown speed c. I don't know the number, I'm not saying it's light, I'm simply saying we now are going to have a car that travels with the speed c with compared to you guys. Okay? Okay. Special case of this general rule. What if you guys look at something that goes with this strange velocity c that came out of the derivation? Then how fast do I see that same thing go? UA, that's c. Plus or minus v. Yes. 1 plus or minus UA, that's for you guys is c, that's v over c. So far so good? Let's take the upper c out. Algebra. This combination, I happen to know is the number 1. It's some number divided by itself. So our formulas that we found are telling me that, yes, velocities add in a very strange way, but there's one particular velocity that if somebody sees it go with c, then the other guy in a different frame B also sees it goes with C. That's a direct mathematical result of this. And last week, We had to postulate this by Maxwell's equations. Now it's a consequence. It's a result. We don't have to assume it, we don't have to measure it. It's an immediate result of the mathematics we have done from inertial frames. C is invariant. By mathematical deduction. So how cool is that? That means Newton, who knew about the inertial frames, had he done this calculation, we only use high school algebra at the end of the day, he could have concluded this. Way before people were able to measure electromagnetism. He could have already known about relativity. Dumb Newton, didn't even see that. By the way, Einstein also didn't, right? This came a few years later. Yes?
But this only says that there is a speed you can't go faster. That doesn't necessarily say it's
No.
the speed of light.
Careful. It does not say you cannot go faster than this.
No,
That happens to be true.
No, sorry. It means if you there's no speed, so whatever you add to it, you get the same speed back. But
Yes.
it doesn't say which speed that has is or what has that speed.
I agree. So from this derivation, one can deduce that nature has built in this special speed. It's built into inertial systems, so I'm really only half joking when I say Newton could have known this. Of course, in retrospect, everything is simple, but it was already in there. But you're right, it doesn't say what its value is, and what in nature, if anything, actually travels with this speed. And that part, of course, is up to experiment. Okay, so we have now arrived, using this derivation, exactly at what last week was our starting point. And I hope with this derivation that you now understand that C is a property of space and time itself, not of light. We got there without using light. It's a deep thing of nature. Okay, and in our final moments, let me say two more things. I'm going to erase this. Two additional consequences of these Lorentz transforms that we have now found based on inertial systems. One of them, and we will work this out in tutorials, is a third property of space and time that in my tutorials we sort of brushed upon. I mentioned it, and maybe some in the Brecht tutorial did as well. This is now the full set. And as special cases of the full set, you get your time dilation and Lorentz contraction. Fine. There's a third effect. It's called loss of simultaneity. If two things happen, exploding firecrackers, at the same moment for one person, so delta t is 0 for one person, how much time is there between the exploding firecrackers for the other person in a different inertial frame? If this is the only rule you know, you would say, well, 0 for one is also 0 for the other. That's fine. But this is a general set. If nobody sees a firecracker explode at the same location. Let's see what happens. If two firecrackers explode in the A frame at the same moment. So they could be apart. One over here, one over there, and they explode in your frame, pang, at the same moment. Delta TA is 0. Then delta TA is 0, but delta TB is not. If the two firecrackers were not at the same location in your frame, then in my frame, the B frame, I will not see them explode at the same moment in time. And again, this is not because I had to wait for the explosion to reach my eye before I know about it. We got rid of that problem with not using light at all. It's a consequence of space and time itself. Two things happening at the same moment in time for one frame is not necessarily the same moment in time at the other frame. How much are they different? Depending on how fast you and I are moving with respect to each other, depending on V and whether in which direction we are moving. That's loss of simultaneity. That's one. Exercises to follow on that. Final one. Here's the real beauty of things. Let's take two exploding firecrackers again. Just my favorite example of two events. You measure when they explode. How much time in between you measure delta TA? Probably non-zero. You measure the amount of distance between them. Generally non-zero. I want to know my numbers. You know how to do that. Take your numbers, plug them in here, you get my numbers. Your amount of time is not my amount of time, my amount of space is not your amount of space. That's what the Lorentz transforms tell you. But here's a cool thing. Let's take your numbers for the amount of time in between, square those, multiply them with this special number c squared. Subtract from it the amount of distance that you see between the two events, and square that. It's like Pythagoras' theorem, but instead of adding, you subtract. Okay? Now, I, in my frame, the B frame, will measure a different amount of time between the explosions, delta TB, and I will also measure a different amount of distance between the exploding firecrackers, delta XB. But if I take my numbers, c squared with a minus, whatever comes out of this combination will be the same as what you got out of your combination. Your delta TA is not my delta TB, your delta XA is not my delta XB, but this particular combination is always the same. In other words, this combination is again what you would call invariant. No matter which frame you go, no matter how much you try to go to different inertial frames, delta T and delta X will change, but this combination will always stay the same. So, this statement, if you don't believe me, by the way, you don't have to, plug in delta TB and delta XB, these two, plug them in here, and these become numbers in delta TA and delta XA, work out the algebra, you will get back exactly the left-hand side. So I'm not saying something new, I'm just using the same rules and noticing that this is true. This combination in the rest of the course is what we call the Minkowski line element. That's fancy words for saying time and space might be different between observers, but a particular combination stays the same. Again, I repeat, nothing new here. It's just the rules we had, where this is a mathematical consequence of that. And that's cool, because now this is geometry. It's Pythagoras' theorem, except with the minus sign. And nature apparently has space and time rules that allows Pythagorean theorem, but with a minus sign. And the Pythagorean theorem is a statement about geometry, how space, time, and the other three dimensions are related to each other. So by going from here to this observation, we have turned our algebraic understanding of space and time, if you want, into a geometric understanding of space and time. We will see this much more next week because I'm going to use this part and really work out the resulting geometry of it, but I want you to have already seen it. Just for comparison, here's normal geometry. Yes? What is the value for the S squared?
dy squared plus dx.
Yeah, this is Pythagoras theorem, right? This is in space. By the way, if I change this angle, alpha, I make the S stays the same. So the S, this number stays the same, but I'm going to change the angle. What happens to the X?
Larger.
Becomes larger. But what happens to dy? It's shorter. If I change the angle and the S squared has to be the same, that means the X gets bigger and dy has to compensate by getting smaller. Okay. The S squared, sure, let's put a C there. Our new Pythagorean theorem. Yes? New type of triangle, where the hypotenuse is now with a minus. I make alpha smaller, but I keep the S the same, because that's what this rule says. The S should always be the same number. I make the alpha smaller, but the S has to stay the same. What happens to the X? Let's go the other way. Let's make it bigger. What happens to the X? becomes shorter. What happens to dt? It has to become larger. So space apparently becomes shorter and time stretches out to make this combination work out the same. Yeah, that's what we saw last week. Time dilation stretches and space squeezes. We will work this out in much more detail, but I'm simply saying that these rules put into geometry, the new Pythagorean theorem, actually graphically shows you the Lorentz contraction versus the time dilation. Nothing new here, it's what you knew, but just put in a mathematical, in a graphical way with the triangle.